Alright, so in this video I'm gonna be explaining another important article about model editing, and the title of this paper is Editable Graph Neural Network for Node Classifications. This paper in ICLR 2024 is very important. So, although graph neural networks have achieved significant success in various graph-based learning tasks such as credit risk assessment in financial networks and fake news detection in social networks, the trained GNNs can still make errors. These errors can potentially have a severe negative impact on society. Model editing, which corrects the model behavior on wrongly predicted target samples while leaving model predictions unchanged on unrelated samples, has garnered significant interest in the field of computer vision and natural language processing. However, model editing for graph neural networks is rarely explored, despite GNN's widespread applicability. So we first observed the existing model editing methods significantly deteriorate prediction accuracy up to 50% accuracy drop, while a slight accuracy drop in a multi-layer perception. The rationale behind this observation is that the node aggregation in graph neural networks will spread editing effect throughout the whole graph. This propagation pushes the node representation far from its original one. Motivated by this observation, we propose editable graph neural networks, a neighbor propagation fee approach to correct the model prediction on misclassified nodes. Specifically, eGNN simply stitches an MLP to underlying GNNs, where the weights of GNNs are frozen during model editing. In this way, eGNN disables the propagation during editing while still utilizing the neighbor propagation scheme for node prediction to obtain satisfactory results. So you are familiar with this graph convolutional network here, that we have this node embedding at layer L plus 1 is updated using layer L. And the goal of model editing is to alter a base model output for misclassified sample. For example, this is a hard example. For example, in curriculum learning, we call these hard examples because they have a low uncertainty, and so we want to fix them. So this is the architecture. You know that in the blue, we fix the backbone of GNNs in blue, while only update the small MLP in the orange during training. So the good thing, we don't touch this GNN. So it is fixed, it is frozen. We only try to learn this trainable MLP, which is the additional thing that we put into our model. And so we call this GNN pre-edit model, and the overall after addition we call it post-edit model. But know that the gradient flow is on this line only, because the other line is fixed. We have frozen the weights. So it's a very good trick to quickly fix your hard example. You have some x hat, y hat pair input and label that is not classified well. We want to fix it. And we use the KL divergence. So the KL divergence between the output of their predictions of MLP and GNN, if we reduce it, then we have a good locality loss. We have a reduced locality loss. And same for task. We are not. We are an edited model, so we condition on the edited model. So before editing, just quickly I review it again. We first stitch a randomly initialized compact MLP to the trained GNN. We then stitch the MLP with the trained GNN. So we denote this MLP by this G5. So we calculate the true loss based on the prediction, the task-specific loss, and the locality loss. So that was the whole idea of this paper, and the rest of the thing is just some analysis. The rest of them is just analysis.